Paul again, and we're looking at the Minesweeper and our algorithms lesson. So, placing the mines. This is a pretty simple algorithm, but there's interesting things that you can get stubbed on. So let's look at first one here. So, the mine placing algorithm uses the inner while loop on line 4 to look for open spaces to put the next mine. Is the inner while loop guaranteed to stop? This was a sample piece of code. That one got the first example. This is exactly the way it looked. So for mine in range mines, so if I'm asked to place 25 in our current example, that means this number is going to go 0, 1, 2, 3, 4, 5 up to 24. So this loop will run 25 times. And we're coming up with an X and Y location, or a column and row. That's the way this code originally done here. And we're going to index the row and the column, because when we're indexing lists of lists, the outer one's going to be the row, and then the next one's going to be the column. So, and this loop's saying while it's equal to mine. So what's going on here? We want to place a mine. Okay, so we're coming up with a random location. And then we're saying, while this location is a mine, pick more random numbers. It's like, wait, what's going on here? So it's a little bit of a funky algorithm. So let's suppose that you're placing the first one. Well, the while this is equal to mine should be false because everything's empty. So the first time you do this, so most of the times this loop will run, this will be false. This first case will be false, and it will just end up placing the location X, Y, and we'll place that mine. So this code's a little bit weird because we're setting X, Y here to an initial set of random numbers. And then it turns out it says like, well, if those aren't good, go ahead and pick another set of random numbers. So this is kind of like, I guess I'm going to put a little loop on here. This kind of algorithm is not making me happy. This is very sad. Because we're assigning multiple places, we're using a while loop in a way that it almost never runs in the ideal case, unless you have a lot of mines. So, but let's imagine something. If I was going to place 400 mines or 500 mines, or let alone 401 mine in a field that's 20 by 20, that 401, there's nowhere for it to go. The random number could run forever, and it will never be able to find a new location that doesn't have one. I mean, once every cell is filled up, there aren't any. And that's not obvious when you look at the code. So this kind of has a hidden potential infinite loop in here. So the answers were yes, it will always eventually find a spot to place all mines. And so we're saying like, no, it can't be that, because if there were more mines than there are the width and height, it won't work. No, it could not. It could become an infinite loop if there are a lot of mines and the random numbers are not distributed. Yep, that's definitely the case. All right. Next one, this mine placing algorithm only has one loop. So this is a different one. This is what the code's modified to be now. But the loop has two conditions to stop. Is the loop guaranteed to stop? We're trying to, so that, remember, algorithms are measured both in terms of correctness and efficiency. If it never stops, it's not correct. That's bad. So we're going to see, this is one characteristic. Does it stop? And is it going to stop in a reasonable amount of time? So we're going to be given a number of mines, and we got rows and columns. So I'll ignore this max tries for just a second. But so while mines is greater than 0, and so it's going to come in perhaps, say, like, for example, 25 in our sample. This is the way you might write something if you're taking a test with your pencil. And if grid RC is not equal to mine, set it. So now I can see it's being set one location. We're getting one set of random numbers. If it works, because there's not something there, we'll go ahead and set it, and that's good. And now we're going to decrement mines. So if I'm looking at this code, I see that mines is modified in one place, and it's decremented. And when this reaches 0, it's like we've placed all the mines. So then this little piece right here where it says mines greater than 0, that will become false. And so this while there's still work to do and we haven't tried too hard will fail. And because we've done all the work we need to do, and it'll return and everything's happy. Now the other part that's in this code is something that's trying to prevent the infinite loop. So you can't be perfect about this. Let me write that a little cleaner here. But we have a variable called max tries. And that says like how many times. It looks like I'm erasing over this other piece. There we go. Max tries. So this is like, we're not going to try any harder than this. So this is an example of an algorithm that's going to fall into the good enough scenario. And if we can't find something, this is what it here. It says like, okay, we went ahead and tried. We picked a random number. If it works, great. Set it up. We're done. If not, we're going to decrement the number of tries we're allowing ourselves to take by 1. And so this was just a heuristic. I just picked it, but rows and columns times 2. So it says, look, we're not going to, doesn't matter how many minds you ask us to put. We're not going to roll the dice or call a random number more than 400 times 2. So more than 800 times. That's an awful lot of times. So the short of this answer to this one is the loop going to stop? Guaranteed to stop? And the answer is yes. And it is. And I think that the next question talks about that. Why is it? Well, this one, nope. There is no loop. That would just be one of those examples of the throwaway answer. And I just trust it more. That's kind of, that's a throwaway answer too, so it can't be that. So we can kind of rule it out. But both branches of the if statement will move a variable that stops one of the variables that will stop the loop closer to its exit condition. So let's look at that code just for a second. All right. So I got 2 clauses in this while. We got minds greater than 0. We got max tries greater than 0. And if either one of those becomes false, then the and expression will become false and the while loop will stop. So can we convince ourselves that those 2 times, it's always going to be the case that 1 or 2 of those will hit false. And if you look at your code, it's like, well, okay. You try to look at what lines do you know have to run. And it's like, well, this one has to run. The row and the column line has to run. The if is always going to run. Now we're in an if and an else. And so what you know from an if and an else is one section is always going to have to run. It's either going to be the first part, I'll call it A, or the second part, B, right? The if or the else. It has to do one or the other. There's no other options. And we can see that in one case, minds. Oh, man. I wonder if I can do that. Control Z. Z. I hate it when it kicks into that mode. That's okay. Right. Look, right there. We are. Okay. So it has to do one of the 2, and in one branch in A, minds is going to get closer to 0, and the other one, max tries, is going to get closer to 0. And so you can look at that code and you can convince yourself. Proving is a little bit harder mathematically, but you can pretty much convince yourself that it's going to have to exit one way or the other. All right. So the answer to that one was both branches move something closer. If you can't tell in a loop how it's going to exit, then that's bad news. All right, if the algorithm is the algorithm guaranteed to place all minds, no matter how many are requested? Okay, this is a setup. Anytime it says computers always calculate enter correctly, let's see, that doesn't sound true. No, it will place at most 50 minds. It's like, well, wait a second. Was there a 50 anywhere in that code? No, that doesn't make sense. See, so that doesn't look right. This one, I'm pretty sure I'm going to put a question mark. I don't think so right now. No, if asked to place a lot of minds or more than will fit, it will eventually give up. I think that word's eventually. That's that max tries bit. And then I'm ready to get out of the shelter in place. I want to see my friends. Well, of course. Yeah, that one's going to be true. Turns out that one's true. I gave you credit for both of those. And then this one is definitely false. So unless we're on here. Since this is running there, I'll go ahead and load up the code just real quick. Just to show you an example of a piece here. So I'm going to bring the screen up just to see something here. So let's make this grid a little bit smaller. Tiles. Rows and columns, 15 by 15. That's smaller than the 20. That's going to be good. So let's suppose I'm going to place 30 minds. And this code here, I've tweaked it just a bit. So when we're placing that mine, when we're placing them, I think I have it in this code. So let's look at here. When I draw this, I can actually prevent it from showing the tiles at all by changing that to a 0. And then I think I have place. There we go, place mines. Oh, that's where it's going to place them, but let's go ahead and find the place mines function. There we go. Okay, I added a print statement here. I'm going to highlight that with our little scribble. It says, whoops, 1 is already there. So in that if and the else, you know, there's that if and the else. This is in the side. It says we couldn't find anything, but we bumped max tries. So if we ran this program here, play, come on. Takes a little longer to run when it's doing that. So look, I already got that message. It says, oops, 1 is already at 1,7. So at row 1, column 7, so that's like, you know, count it down here. It's like 1, 2, 3, 4, 5, 6. Oh, excuse me, row 1. Yep. Row 1, 1, 2, 3, 4, 5, 6, 7. That's this guy actually, right there. So that random number came up twice. First time it placed it, the second time it says that won't work. Now, if I switch this up to a much higher count, you can see, so it's like instead of 30, let's suppose I go to like 50 mines. This would be a very hard game to play. All right, it's running up there. Now we see that there's a lot of oopses. Because as you're rolling the dice, there's a fair chance that you're going to end up playing a place of mine where there already was one. So you can say this isn't a perfect solution because that gets worse. And if I bump that number up considerably higher, so suppose I said I want 500 mines. That's actually more, you know, just what is on here. 15 times 15 is 225, right? So if I said that's over twice as many mines as the game could even hold. So let's see what happens. Do you think it's going to have one in every single cell? Let's look at it. Look, it doesn't. So you keep rolling the dice, so to speak, using the randent function, and it's not able to guess every one. And so we rolled it more than twice as there are as many tiles. And so that's kind of a problem with this. If you say like, well, what gives here? Shouldn't, if I did it 255 times, 225 times, shouldn't it fill it all up? Well, it wouldn't if you're just using the random function. You might do something that says like, hey, if a man's already where it is, maybe I'm going to start looking around to find the nearest spot that doesn't have one. And that might be a viable solution. It'll take a little bit more code, but that way it's guaranteed not to rely on the random number function. So we've done a lot of looking on that. I think that's the last question on the test. So these are great days. I'll go ahead and submit a new version, and best wishes on it. And God bless you guys.